Let's talk about applying our understanding of equilibrium to weak acids. So we can measure acid strength by looking at the equilibrium constant when an acid reacts with water. The equilibrium constant for that reaction is called the acid ionization constant, or Ka. The larger the Ka, the stronger the acid, because you have more products than reactants. And so if you have a larger Ka, you're going to have a stronger acid because more of it will ionize in water. Here's a table with Ka values for some monoprotic weak acids at 25 degrees because, again, Ka is temperature dependent. And this table is mostly for your reference, table 15.5. And we will use some of these Ka values in upcoming questions. Water itself is an extremely weak electrolyte. About 2 out of every billion water molecules will form ions through something called auto-ionization. So you have 2 water molecules reacting to form an H3O plus and an OH minus. So all aqueous solutions are going to contain both H3O plus and OH minus. In pure water, those concentrations are equal to each other, and their concentration is times 10 to the minus 7th molar at 25 degrees Celsius. The product of the H3O plus and OH minus concentrations is always the same number. It's called the ion product of number, or Kw, or the dissociation constant. So at 25 degrees, Kw is 1 times 10 to the minus 14, which means if you measure one concentration, say the H3O plus, you know Kw, you can always find OH minus, because H3O plus times OH minus is always equal to 1 times 10 to the minus 14 at 25 degrees Celsius. They're inversely proportional to each other, so as you increase your H3O plus concentration, you're going to decrease your OH minus so that the product can stay constant. So we can practice, determine the H3O plus when the OH minus is 2.5 times 10 to the minus 9 molar. So we know that our H3O plus times our OH minus is equal to 1 times 10 to the minus 14th. So our H3O plus is going to be our 1 times 10 to the minus 14th divided by our 2.5 times 10 to the minus 9th, which gets me an H3O plus concentration of 4.0 times 10 to the minus 6th molar. Now we can use that to talk about pH. pH is a scale that's derived from the concentration of the hydronium ion H3O plus, and it can describe how acidic or basic something is. So the pH is the negative log of the H3O plus concentration. This lowercase p here always means negative log. The pH of pure water, I talked a couple slides ago about how the concentration of H3O plus is times 10 to the minus 7, 1 times 10 to the minus 7. So the pH of pure water is 7. And you need to know your H3O plus concentration to find your pH. And then if you know your pH and you want to find your H3O plus, you can just do the inverse of your log button, and it'll be 10 to the negative, and then plug in the pH. The pH scale, if we look over here, anything less than 7 is acidic, and anything greater than 7 is basic. And then anything right around 7 is considered neutral. Now, just so you know, for significant figures and logs, when you take the log of a number written in scientific notation, the number before the decimal point comes from your exponent, And so if you want to use significant figures with logs, you need to count the number of sig figs is the number of digits after the decimal. So here we have 2 significant figures, and so we write down 2 decimal places for our log. pH is going to tell us about how acidic or basic a solution is. And remember that 1 pH unit corresponds to a factor of 10 difference in acidity. Our normal range is from 0 to 14, although technically pH can get negative, which is very acidic, or larger than 14, which is very basic or alkaline. And so pH 0 is a H3O plus concentration of 1 molar. pH 14 is a hydroxide concentration of 1 molar. So let's practice. Determine the pH of a solution that has a hydroxide concentration of 2.5 times 10 to the minus 9th molar. There are 2 ways to go about this, and I'm going to show you both of them. The first way is we know our Kw is our H3O plus times our OH minus. So our 1 times 10 to the minus 14 is our H3O plus times 2.5 times 10 to the minus 9th. So we can find our H3O plus is equal to 4 times 10 to the minus 6th. We did that part already. And then to find our pH, we take negative log of 4 times 10 to the minus 6th, which is 5.40. The other way to do this is our pH plus our pOH, which is just the negative log of the OH concentration, is equal to 14. So my pH plus, that's a plus, sorry, the negative log of 2.5 times 10 to the minus 9th is equal to 14. So my negative log value here is 8.60 is equal to 14. And so my pH is equal to 5.40. Gets you the same place. It just depends on when you want to deal with the log. All right, now we can kind of work backwards. Determine the hydroxide concentration of a solution with a pH of 12.40. Again, I would recommend pausing the video, working this through, and then I will do it both ways here. So if my pH is 12.40, that means my H3O plus is 10 to the minus 12.40, which is 3.98 times 10 to the minus 13. And that means that times my hydroxide, so H3O plus times OH minus is equal to 1 times 10 to the minus 14. So my OH minus is 2.51 times 10 to the minus 2. My other way of doing it is taking 14 minus 12.40, which gives me 1.6, which is my pOH. Then I can take 10 to the negative 1.6 and get the same answer, 2.51 times 10 to the minus 2. So either way will get you there. Here's pOH, which I've been talking about. It's the negative log of the hydroxide concentration. And here's the equation I've used on the past couple slides. The pH plus the pOH is equal to 14. And for basic and acidic, it's the opposite of what it is for the pH scale, see how they run in opposite directions. So let's do another practice. Determine the pOH at 25 degrees Celsius of a solution that has a H3O plus of 3.7 times 10 to the minus 8th. I'm just going to do this the pH way. So my pH is the negative log of 3.7 times 10 to the minus 8th. So my pH is 7.43, which means my pOH is 14 minus 7.43, which is 6.57. Okay, one more p-value we can use is the pK. That's a way of expressing the strength of an acid or base. Again, the lowercase p just means negative log. So we can have tables that list the pKa values of acids instead of the Ka. The pKa is simply the negative log of the Ka. The stronger the acid, the smaller the pKa value. A larger Ka gives you a smaller pKa because of the negative log. Similarly, we can do a pKb. The Kb is the base dissociation constant, and a pKb is just the negative log of that. Now, in an aqueous solution, we have two sources of H3O+, the acid and the water, two solutions of hydroxide in an aqueous solution of a strong base, that should say base, the base in the water. For a strong acid or base, the amount that water is contributing to that is negligible because all the acid from the strong acid, if we think back to Le Chatelier's principle, is going to shift our equilibrium for Kw so far that the value from water is going to be insignificant unless you're in a very dilute solution. So a strong acid or base, if you want to find the pH, you can just take the negative log of the concentration of the strong acid, or for pOH and strong base.